increase from P8 to P10 is 10 units, 47 to 57. And we had 2 transitions to get there, P8 to P9, P9 to P10. So my common difference has to be 5, right? I went up 10 units over 2 transitions, so each transition has to be 5. So I'll type a 5 in here. Do it. Check. Okay, so good. I got my common difference. And then P0, that's your initial value, right? So that means I have to work backwards from P8, subtracting 5, because I'm going backwards, until I get P0. So that means that P7 would be 42, P6 would be 37, P5 would be 32, P4 would be 27, P3 would be 27 minus 5 is 22, and that was P5. I lost track. 7. Okay, thank you. Great. All right, so then when you have to give the formula, the general formula is P0 plus ND, but each example has its own P0 and its own D, right? And that's what it asked you for in A and B. They were helping you get the pieces of the formula. So it's going to be 7 plus 5N. Yeah, so you can't write down the general formula. That's the formula that is true for every possible problem, but each problem has its own P0 and its own D. So yeah. Mm-hmm. Yeah. So let's, I went 32 to 52, which is 20. Oh, and I went up by 5 spaces, so 4. Yep. Okay. And then P0, going backwards by 4. 12, I think. Yep. Okay, so then if I put P0, oh, okay. P0 plus ND. Oh yeah, and you're like, well, that is what I did. Yeah. Yeah, so so yes, that's the general formula, and then each problem has its own P0 and its own D that you have to plug in. Yeah. All right, so that should help, I think. All right, so moving to class 19. We're still in mini excursion 3, population growth. And last class we talked about linear growth models. So that's where you add the same amount at each transition. So you have a common difference. When you subtract any 2 successive populations, you always get the same amount. So linear growth results in what we call an arithmetic sequence. So they're almost synonyms, linear and arithmetic, like mean basically the same thing. Okay, so this was last class's stuff. Always add the same amount. So today, we're going to talk about a different kind of growth model called exponential. And this is where you multiply by the same amount at each transition. Okay. So instead of adding the same thing to each population, you're going to multiply each population by the same number. And exponential growth results in a geometric sequence. So they're like kind of synonymous, geometric and exponential. So if we have a rabbit population that starts at 1,000 and increases by 20% per year, let's find out how many rabbits there are after 1 year, 2 years, 3 years, etc. So we'll start by making a little table. So we have n, p sub n. So in year 0, we have 1,000 rabbits. Okay, so we like to start our sequence with 0 instead of 1, like we learned to do before because that means like at the beginning, before a year has even passed, right? Our initial population we call P0. All right, so 1 year later, I need to increase 1,000 by 20%. So that's its own kind of math problem, right? How to increase a number by 20%. So I'm going to do it on another page. So I need to increase 1,000 by 20%. Okay. So in general, how do you do this? 1,000 times 1.2. There's multiple ways to do it, right? So one of the quickest is to multiply 1,000 times 1.2. Now, why 1.2? 20% in addition to the whole, right? Because you're increasing by 20%, which means you're keeping 100% of what you have, that's the 1, and increasing it by 20%. 100% plus 20% is 120%, and as a decimal, that's 1.2. So another way you can do it is you can do 1,000, say, well, I have 1,000, and I'm going to add 20% of 1,000. That's kind of a nice way to do it in your head, right? Well, 20% of 1,000 we can do in our heads. How would you get that in your head? Move the decimal place. So 10% of 1,000 would be 100. 20% of 1,000 would be double that, so it would be 200. That's like a quick way to calculate a tip in a restaurant. Move the decimal place 1 to the left and then double it. Gives you 20%. Okay. So this would be 1,000 plus 200, which is 1,200 rabbits. That's the same thing you get when you do 1,000 times 1.2, 1,200. Okay. So increasing a number by 20% you can do by multiplying by 1.2. And we get 1,200 rabbits. Okay, and then a year later, now I'm going to increase what I had in year 1 by 20%. So I need to take 1,200 and increase it by 20%. So I'm going to multiply 1,200 times 1.2. And I get 1,440. And in year 3, take 1,440, increase that by 20%. So I'm going to multiply by the same number again. That's what makes this exponential growth, is that I'm multiplying by the same thing at each transition. So I get 1,728. So if I want to know the population at year n, how could I figure it out? Well, that would give me the population at year 4. But if I want to know the population in any general year, like if I wanted to know the population in year 20, what would I do? Yeah, a recursive one would say, take the year before, right, and multiply it by 1.2. So my population the year before the nth is the n minus first, and I would multiply that by 1.2. So there's my recursive formula for the population in year n. I would say, well, take the previous year, multiply by 1.2. Population of the previous year, to increase that by 20%, multiply by 1.2. And when you're giving a recursive rule, you probably should give the initial population. So whoever is following your rule has something to start with. All right, now the explicit formula for the exponential growth is a little bit trickier. Close. That's really close. That would be if you add 1.2 each time. because 1.2 times n means 1.2 plus 1.2 plus 1. It's repeated addition. How do we notate repeated multiplication? An exponent. So I want to multiply by 1.2 over and over again. I use an exponent.
So it's 1 times 1.2 to the n power.
Yeah, that's fantastic. Yes. So P sub n would be, say, we'll start at 1,000, and we multiply at each transition. You multiply by 1.2, and do that n times. Multiply over and over. The way we write down multiply by that same number over and over again is we use an exponent. And let's just show it in the table just so that if there's any lingering confusion. 0, 1,000. So we do, to get year 1, you would take 1,000 and multiply by 1.2, right? Instead of actually calculating it, I'm just going to leave it like that, 1,000 times 1.2. And then in year 2, you take what you had in year 1, 1,000 times 1.2, and you multiply it by 1.2, right? So I'm just not doing the calculation out. Instead of writing 1,200, I'm leaving it written as 1,000 times 1.2. And then to get to year 2, you take what you had in the previous year, multiply by 1.2 again. Year 3, I do 1,000 times 1.2 times 1.2. That's what I had in year 2. And then you multiply by 1.2 again to increase by 20% for year 3. So then you keep doing that, and you see that the number of 1.2s always matches the n, right? 3 1.2s. So this would be 1,000 times 1.2 to the first, 1,000 times 1.2 squared, 1,000 times 1.2 cubed. So for the n, I would do 1,000 times 1.2 to the n. Right, because my n value always matches my exponent. So there's my explicit formula. All right, so that number 1.2 that we've been using a lot, that's we multiply each population by to cause our 20% increase. We call that the common ratio. Okay. So just like the number that you add at each transition in linear growth, we call that the common difference. This one, the number we multiply by at each transition, we call the common ratio, because it's the value of the ratio of the current population to last year's population. So if I take any two populations, let's write down my table again. So I have 0, 1,000, 1, 1,200, 2, 1,440, 3, 1,728. If you take any two successive population sizes and divide the bigger by the smaller, we're always going to get 1.2. So 1728 divided by 1440, 1.2. And 1440 divided by 1,200, 1.2. 1,200 divided by 1,000, 1.2. So we call that number that you multiply by the common ratio. We usually use the letter R to represent it. Okay, so these are the general formulas for exponential growth. Again, you don't need to memorize these because we just came up with two formulas for a particular example, a recursive and an explicit, without knowing the general form, right? So, but formulas can be handy to have. Always something to fall back on if you don't know what to do. So in general, if you're writing a recursive formula, you give the starting amount, and then the recursive rule is the population in any time n is the population at the previous time, n minus 1, times that common ratio. And for explicit, you do the start amount times the common ratio to the n. So for us, we went, okay, well, P0 is 1,000, and P sub n was P sub n minus 1 times 1.2. And for explicit, we said P sub n is the starting amount, which is 1,000 rabbits, and we multiply by the common ratio, 1.2, to the n. All right, so here's a different kind of setup that also involves exponential growth. We have the Earth's population was about 6 billion in the year 2000. And assuming the population doubles every 45 years, predict the population in 2045, 2090, 2450, and 2900. So discuss in your groups. All right, so let's see. We've got the year n and the population P sub n. In year 0, my population is 6 billion. And rather than writing out 9 zeros to represent billions, I'm going to just put a little b for billions. Okay. So at my next transition, which would be, my next transition I'll call 1, which is actually the year 2045. I'm going to double. So I have 12 billion. And then my next transition, which is 45 years later, which is 2090. Would be 24 billion, right? Okay, so every 45 years, I double. So my next doubling is going to be at 2,135, which would be 48 billion. Right? So to get to 2,450, I'm going to have to put a lot of entries in this table. Or I could try to think about how many entries I'm going to have to put in to get to 2,450. 8 more, right? So I would say, well, from 2,000 to 2,450, that's 450 years, right? So 450 years. How many sets of 45 is that? 10. That's 10 sets of 45 years. How do you figure that out? How do you figure out how many sets of 45 there are in 450? Divide. 450 divided by 45, you get the 10 sets. So that means you're going to double 10 times. Population doubles 10 times. Okay, so I could say, well, I'm going to take 6 billion, and I'm multiplying it by 2 times 2 times 2 times 2 times 2, 10 times, which I could write as times 2 to the 10th. So 6 billion times 2 to the 10th. 2 to the 10th is 1,024 times 6 billion is 6,144 billion, which is actually 6.144 trillion. 6,144 billion. Okay, so that's my population in 2,450 trillion. To get 2,490, I'm sorry, 2,900. I would think to myself, okay, so from 2,000 to 2,900, how many years have passed? 900 years. Starting again at 2,000. From 2,000 to 2900, 900 years have passed. And then I ask myself, okay, well, how many sets of 45 are there in there? And I would go, well, 900 divided by 45 is 20. 20 sets of 45 years have passed, so that means I want to take my 6 billion and double it 20 times. Okay, so for 2900, I'm going to do 6 billion and double it 20 times, and that's going to come out to 2 to the 20th times 6. 6,291,456 billion, right? 6,291,456 billion people, right? So that is actually, well, that's trillions, quadrillion. What comes after quadrillion? Quintillion. 6 quintillion, 291 quadrillion, 456 trillion. No, that should be billion. It's quadrillion. 6 quadrillion, 291 trillion, 456 billion. Maybe I'll just write it down. 6 quadrillion, 291 trillion, 456 billion people. That's way overcrowded, right? It won't fit. Yeah. So those are all different ways of expressing the population in the year 2900. And then there's 2,450. So the procedure we used was figure out how much time has passed, figure out how many sets of 45 years that is, and that's how many times you double. So if I want to do a harder one, like 2,120, why is this problem harder?
You got to figure out a fraction of the growth.
Yeah, because it's not, this isn't a multiple of 45 years. Yeah, 120 isn't a multiple of 45. So you say, but we could try to follow the same procedure and see what happens, right? 120 years divided by 45 is 2 2/3, right? 2 2/3. So that means I'm going to double somewhere between 2 times and 3 times. So if I double twice, P sub 2, which is the population in 2090, right? Would be doubling twice is 24 billion. And doubling 3 times is 48 billion. So I'm hoping whatever I do, it should come out somewhere between 24 and 48 billion. Exactly where is kind of like, well, that's the question. That's what makes this problem hard. So, but let's do the exact same procedure we did before and see if it comes up with something reasonable. So I'm going to take my 120 years and divide by 45. How many sets of 45 years have passed? Yep, 2 2/3. Yep, which is approximately 2.67 sets of 45 years. So what I did before is I took my initial population, 6 billion, and I said, well, multiply by 2, and then I put the number of times that you double as the exponent, because we were treating exponents as repeated multiplication. But what if I just put this here? The number of sets of 45 years, same as I did before. Let's see if it comes out to something reasonable. So I'm going to raise 2 to the 2.67, or 2 2/3, and then multiply that by 6, and I get 38.097. So let's just say approximately 38. 38 billion. Yep, 2 to the 2.67 power, and then multiply by 6. So we get 38 billion. Is that a reasonable answer? Yeah, I mean, it makes sense. It's between 24 and 48. That's because I used 2.666666667, and you used probably just 2.67. Yeah. It's closer to 48 than 24. Does that make sense? Yep, because 2/3, we're doubling 2 and 2/3 times, so it should be closer to 3 times than 2 times. So we have a method that seems to make sense, right? Follow the same procedure as we did when we had a multiple of 45. And now we have raising to exponents that aren't whole numbers. But it generalizes well, still works. Mm-hmm. Yep, we did. Oh, did we? No, we didn't. Okay. Let's do that. So for this particular problem, the population after n years, so we're going to let n be number of years. Number of years since 2000, right? So in general, I'm going to take my starting amount, which was 6 billion, and I'm going to double it some number of times. No, close. That exponent is the number of sets of 45 years that have passed. N is just the number of years that have passed. How do you figure out, given the number of years that have passed, how many sets of 45 there are? Divide by 45. You take the number of years that have passed, like if it was 120 years, we divided that by 45 to get the number of times you double. So if 200 years have passed, I would take my 200 and divide by 45 and say, well, that's the number of times I need to double the population, because there are 4.4444 sets of 45 years in 200 years. So P sub 200 would be 6 billion times 2 to the 4.44. So that 4.444, and I'm keeping all the decimals to try to be as accurate as I can. And then multiply that by 6, and I get 130.63 billion. So this is my explicit formula.
I'm confused because you mean in the year 2200.
Mm-hmm. Yep.
Why does it say P 200 then?
It says P sub 200. It's a subscript. That just means.
Yeah, because it's just assuming you know that the starting number is 2000.
Then why are we like for n? Because we're doing like 1, 2, 3, we're doing like.
I redefined n here. N now represents the number of years since the year 2000. So you defined n as the number of sets of 45. And I did too earlier, right? I said, back when I made this table, I let n be the number of sets of 45. But then I said, well, this isn't a convenient way to define n if I'm trying to find the population in a year that's not a multiple of 45.
Oh, okay.
So instead, I said, why don't we let n be the number of years since 2000? So I would change. So I'm changing all these. So instead of this being 1, it would be 45.
Okay.
And this would be 90.
Okay.
Does that make sense?
Yes.
Okay.
That's why you have to.
Yes. Yeah. Okay, so a bank account can be thought of as a population of money that grows, right? That is an explicit formula. This is an explicit. Do you want to do the recursive?
Oh,
Yeah, the recursive, sure. So to find a recursive formula, in general, we would say, well, P sub n would be P sub n minus 1 times something, right? So let's figure out, we have to figure out what that common ratio is. So I could say, well, I need to find out what I multiply by to get from 1 year to the next. So I have to, if I calculate 2 successive years, I could get it, right? So I know P0 is 6 billion. What's the population 1 year later? Nope, that's 45 years later, it's double.
oh.
What's the population 1 year later? Close.
It's one of the exponents.
Yeah, so the exponent, it's going to say, I'm going to take 6 billion and I'm going to double it 1/45th of a time. Right? Take the number of years that have passed, divide by 45. That's your exponent. So
I thought the P1 now would be 45.
nope. P1 means 1 year later, as opposed to 45 years later.
I thought we changed it though, so that N now is,
Number of years since 2000.
yeah, so,
So this is 2001.
oh, so it literally for, so we're not, like, it's not scaled anymore, like it has, like, if P1 is 2001, P2 is
Now it
2002,
goes,
P3.
Right.
now if you were to write that chart, it would go P45, P90, P, if we're going by 45 years. It's like literally.
And so P1 isn't in there.
So to get to the 45th year, the first doubling, you get P45. But it's
Right.
like it's 1 year at a time.
So it's no longer doubling's not really the common thing anymore. If we're
Now
moving.
we're
Right.
to break it down
Right.
to
So we
years.
don't, yeah. To go, we double every 45 years. In 1 year, we're certainly not going to double, right? We go part of the way towards doubling. Part of the way towards doubling. So 1/45th of the way, actually, right? So we do 1/45th, 1 divided by 45, and I'm going to raise 2 to that value. That's how many times I double in 1 year. So I'm going to do 2 raised to that number, and it's 1.0155 about. Oops. So that's the number that I multiply the previous year by. Times 6. 6.0931. So if I have my population in year 0 and my population in year 1, if I divide them, I should get the common ratio. Divide any 2 successive years. So if I do this, my population in year 1 divided my initial population 6, I get that 1.0155. That's what you multiply by each year. So what percent increase does that correspond to? Yearly growth. 1.55% growth. Yeah. So doubling every 45 years. So if I say population doubles every 45 years, that's equivalent to saying my population is growing by 1.55% yearly. No, because this 1 represents 100%. Keep 100%. Grow by 1.5%.
Okay.
Yeah. I know, it is. A lot of like moving the decimal point back and forth, and yeah. I know. So let's sort of summarize what we just said then. So there's different ways of representing P sub n, right? These are going to be two explicit formulas that mean the same thing. Okay, so both explicit formulas. The first one we came up with said that if n is the number of years that have passed since 2000, then you start with 6 billion and you multiply by 2. And then the number of times you multiply by 2 depends on how many years have passed, right? You need the number of sets of 45 years, so we do to the n over 45. Another formula I could write for this would be P sub n is equal to P sub 0, 6 billion, and every year you multiply by 1.0155. So we would do that n times. So these two formulas will give you the exact same thing. So let's check one. Let's try 45 years, right? We know that if n is 45, that this should come out to 12 billion. Let's see if this one gives us 12 billion. If n equals 45. So here's my 1.0155 number. I'm going to raise that to the 45th. And I get 2. Right? So then I multiply by 6 and I get 12. All right, let's think about a bank account as a population of dollars that multiply. I want you to discuss in your groups for a few minutes. Which would you rather? $1 million handed to you right now, or a bank account that starts with 1 penny in it and doubles in value each day for 30 days? Take a few moments to consider. It's a big decision. So, on the one hand, we have $1 million. Hard to turn down, right? And on the other hand, we have 1 penny, a single penny, but my bank is going to double the value of that penny every day for 30 days. 1 month, just 1 month, I get this doubling deal. So I'm starting with 1 penny, 0.01, and I'm going to double it, which means times 2, right? And how many times do I double it? 30 times. So I raise to the 30th. Because multiplying by 2 30 times means we write that as 2 to the 30th. So if I do 2 to the 30th, that's already a really big number. And then I'm going to multiply that by 1 penny. And I get $10,737,418. 37, 418 and 24 cents. So 1 million or 10 million, right? Take the penny. Yeah, this is called compound interest. I mean, this is an extreme example because no bank account is going to pay you 100% interest, which is doubling 100% interest daily. That's crazy. But there is this is an example of compound interest, and it shows how powerful compound interest is. And Albert Einstein once said that compound interest is the most powerful force in the universe. Growing, which basically means exponential growth. Growing by a multiple is one of the most powerful forces in the universe. Yeah, it is. Bacteria, which those crazy killer bacteria and viruses that get into hospitals and they can't control them. That's how they grow too. So here's another interesting exponential growth problem. So it's difficult to measure the thickness of a single sheet of paper, but you can figure it out by using the fact that a whole ream is 5 centimeters thick. So how would I figure out the thickness of a single sheet? Divide 5 centimeters by 500. So 5 centimeters divided by 500 sheets is 0.01 centimeters. 0.01 centimeters thick, a 1/100th of a centimeter. All right, so when you fold a piece of paper in half, I'm going to fold your project proposal, Brian. So I have a piece of paper and I fold it in half, and imagining that, you know, there's no air in between, squish them down. How thick is that now that I've folded it? 0.02 centimeters, because the single sheet is 0.01 and now I've doubled it, right? 0.02. So with 0 folds, it was 0.01, right? 1 fold, 0.02. And then I'm going to fold it again. So now it's like folded in quarters like this. How thick is my paper? 0.04. Yeah, doubled it again. And then if I fold it one more time, 0.08, 0.16. So you get the idea, the thickness of your paper is going to double every time you fold it in half. Okay. Let's see if we can come up with an explicit and a recursive formula for the thickness of my paper. So we'll start with recursive. So T sub n, the thickness after n folds, based on the previous thickness, how would I calculate my new thickness? Just double it. So I would do Tn minus 1, the thickness at the previous step, times 2. And then my explicit, I would say, well, T sub n starts out at 0.01. That's my initial thickness. And I'm going to double it, which means times 2, n times. So I raise to the n. Doubling it over and over and over again. Multiplying by 2 over and over and over again is written as 2 to a power. So I do 2 to the n. All right, so we have recursive and explicit formulas. What would the thickness be after 7 folds? So T sub 7. I could make my table. I could just continue my table, or I could use my explicit formula and do 0.01 times 2 to the 7th. 1.28 centimeters, right? That's what I'm measuring in. 1.28 centimeters. So not about that thick for 7 folds. Little still. What about after 1.28? That would be
5 centimeters is 5
yeah,
pieces.
1.28 divided by 0.01. It's equivalent to 128 pieces of paper
After 7 folds.
after 7 folds. Yeah. Yeah. All right. How many folds do you think it will take to reach the thickness of a ream, the 5 centimeters? 9. So if I do 0.01 times 2 to the 9th, if I double it 9 times, two to the 9th times 0.01, 5.12. It's a little bit more, but that's good. So about 9 times. So 9 folds will get me a little bit bigger than a ream. Just 9 folds gets me that thick. Whole ream of paper. Okay, what's the thickness after 15 folds? So I'm going to double the thickness 15 times, so I multiply by 2 to the 15th. 2 to the 15th times 0.01 is 327.68 centimeters. Well, once we get that many centimeters, it might make sense to measure in a different unit, right? Meters, yeah. How many centimeters are in a meter? Anybody know? Nope. 100. Centi means 100, right? So this would be 3.2768 meters. And a meter is about 3 feet. So that's like, I don't know, between 9 and 10 feet tall. That's really tall, right? We took a piece of paper, fold it in half 15 times, and it's taller than this ceiling. We should have started with a big piece of paper. Now it's really skinny and tall, right? So this is a little theoretical because I think it's actually been proven that you can't fold a piece of paper more than 6 times. Yeah, in half, yeah. It gets like too unwieldy. Can't fold it.
If you had a really big piece of paper that was
That you could do it, I know. I don't know. So what if we go 5 more folds, 20 folds? 0.01 times 2 to the 20th. 2 to the 20th times 0.01. 10,485 centimeters. 0.76 centimeters. And again, centimeters isn't a good unit. To change it to meters, you divide by 100 because there are 100 centimeters in a meter. So if I divide by 100, I get 104.8576 meters. About how long is 100 meters? Yeah, 300 feet. It's like a football field. It's like about 100 yards. It's a football field. 1,000 meters. That's crazy long, right? One single sheet of paper, we just had to fold it in half 20 times. It doesn't seem like a crazy number of times. And now it's the length of a football field. Yeah. I know. Exponential growth, most powerful force in the universe.
I would like to see that.
Actually,
Well,
thumbs would probably be the most powerful force.
If you could get it to fold, yeah, I know. Let's see, 25 volts, 0.01 times 2 to the 25th. Just 5 more folds than before. Yeah, it is. 2 to the 25th times 0.01. 335,544.32 centimeters. And then let's probably change it to some more appropriate units. Yep, so divide by 100. It moves the decimal point 2 to the left. 3,355.4432 meters. And we could change this to kilometers because there are 1,000 meters in a kilometer. So if I divide by 1,000, I get 3.355 kilometers. 3.3 kilometers. How far is that? Yeah, because there's like 1.6 kilometers in a mile, I think. Yeah, the kilometers, yeah, so 1.6 kilometers in a mile. So if I divide this number, 3.355 divided by 1.6, it's about 2 miles. just say approximately 2 miles. So we're starting to see why you can't fold the piece of paper more than 6 times, right? Because once it gets so long, I mean, like, how on earth do you get it to fold again? It's too thick, right? But 25 folds gets you 2 miles. The distance from Earth to the moon is 384,403 kilometers. Discuss in your groups, just do a little trial and error. How many times do you have to fold a piece of paper to make it go all the way to the moon? So I changed kilometers to centimeters because that was the units my original problem was created in, with 0.01 centimeters. So you take your kilometers, you multiply by 1,000 to get meters, and then multiply by 100 to get centimeters. So you end up putting 5 extra zeros on the end. So I want to know 0.01 times 2 to what power will get me that many centimeters. That's the number of centimeters to the moon. 41.8. So somewhere between, right, so 41's almost to the moon, 42 passes it. So let's just see, if I do 2 raised to the 41 and times 0.01, that's 219 instead of 384, so it's a little shy. But if I double it one more time, I get 439, so I've passed. So 41, 42. Will get you to the moon. Yeah. And if you don't want to think about it in terms of folding the paper because you can't fold the paper that many times, just think about it in terms of doubling the stack, right? If you have a single sheet of paper and you double the size of the stack, you only have to do it 42 times to get to the moon. I know, isn't it? I'm glad you guys appreciate it. Often I do this lesson and people are like, oh, whatever. So exponential growth is generally not sustainable because we see how quickly it grows, right? You can get really big, really fast with exponential growth. So it's usually not sustainable because resources and food and water and space are always finite. You don't have an infinite number of those things. So a more realistic population growth model would be the logistic curve. And it starts out looking exponential. It starts out growing very quickly. This is what an exponential curve looks like. And then it levels out at some value called the carrying capacity of the environment. So this height right here, we call C the carrying capacity. And I'm not going to delve into the formulas, recursive and explicit, like formulas for this guy. But that might make a really good topic for a project. Your book has this in there, logistic growth, and you could study it and maybe do that as a project if you were interested. So we have an activity that you can start, but we only have 5 minutes, so you could take a quick look at it if you want. Otherwise, that's it for today. And everybody knows